12,800 years ago, something happened to Earth. The planet was warming. Ice sheets that had covered half the world were melting. Humans were spreading, building, creating the first settlements. Then, everything stopped. In the span of maybe a decade, temperatures crashed. The warming reversed. Ice came back, and it stayed cold for over 1,000 years. We call this the Younger Dryas. It's named after a flower, a small Arctic plant that suddenly shows up in geological layers across Europe. Dryas octopetala. It grows in tundra, in frozen places, and around 10,800 BCE, it spread south. Fast. The flower tells us the climate changed. Dramatically, quickly. But here's what keeps scientists up at night. This wasn't a gradual shift. This was sudden. Ice cores from Greenland show temperatures drop 10 to 15 degrees in less than a decade, maybe faster. Some evidence suggests it happened in 3 years. 3 years. Imagine that. You're living through the end of the Ice Age. Your grandparents told stories about the glaciers, but those are just stories now. The world is warming. Animals are everywhere. Plants are thriving. Your people are settling down, building permanent homes for the first time in human history. Then winter comes, and it doesn't leave. Not for 1,000 years. The Younger Dryas lasted from about 10,800 BCE to 9,600 BCE. 1,200 years of reversed progress. The archaeological record shows something stark. Settlements abandoned. Populations crashed. In some regions, humans nearly disappeared. We know this happened. The evidence is everywhere. In ice cores, in lake sediments, in pollen records that show forests dying and tundra returning, in the bones of animals that went extinct. What we don't know is why. That's the mystery that haunts geology. Climate doesn't just reverse like that. Not naturally. Not that fast. Something caused it. Something big enough to throw the entire planet back into Ice Age conditions. Something powerful enough to nearly end human civilization before it really began. The theories are wild. An asteroid impact, a comet exploding over North America, massive volcanic eruptions, the collapse of ice sheets changing ocean currents, solar activity, even a supernova. Each theory has evidence. Each has problems. None fully explains what happened. And here's what makes it personal. We almost didn't make it. Genetic studies show a bottleneck, a moment when human populations dropped so low we nearly went extinct. Many scientists think it happened during the Younger Dryas. We survived. Obviously. But it was close. This isn't ancient history. This is the story of how we almost ended. How fast can everything change? What did it look like on the ground? The evidence sits in ice. 2 miles down in Greenland's frozen core. Scientists drill through time itself. Each layer is a year. Each bubble trapped air from that moment. And the story those bubbles tell is terrifying. The temperature didn't ease down. It fell off a cliff. In 1993, researchers published data from the GIS P2 ice core. They measured oxygen isotopes. These isotopes work like ancient thermometers. The ratios tell you how cold it was when that snow fell. And around 10,800 BCE, something shows up that shouldn't be possible. The temperature dropped 15 degrees Fahrenheit, maybe more, in less than 10 years. Some layers suggest it happened faster. 3 years, maybe 1. Think about what that means. Not a gradual cooling over centuries, not even over decades. Within a single human lifetime, the world transformed. If you were 20 when it started, you were still young when winter became permanent. The ice cores from Greenland match cores from Antarctica, from the Alps, from the Andes. This wasn't regional, this was global. The whole planet lurched back toward Ice Age conditions at the same moment. But temperature is just the beginning. The ice holds other secrets. around the same time as the temperature crash, there's a spike in something else. Platinum, iridium, rare elements that don't belong in ice. They come from space, from asteroids and comets. And right at the boundary of the Younger Dryas, they show up in concentrations hundreds of times normal levels. There's more. A layer of black carbon, like soot from massive fires. It appears across North America, Europe, Asia, in ocean sediments off the coast of California, in lake beds in Europe, always at the same level, always right at the start of the Younger Dryas. Something burned, something huge. In 2007, a team of scientists proposed the impact hypothesis. They found evidence of an airburst, a comet or asteroid exploding over North America. The heat would have been unimaginable, hot enough to melt rock, hot enough to turn sand into glass, and they found the glass. Tiny spherules scattered across the continent, melted droplets of rock that cooled in midair. You only get these from extreme heat. Nuclear blasts create them. So do asteroid impacts. The spherules appear in a layer called the black mat. It's a dark band of sediment found at dozens of archaeological sites, Clovis sites, the people who lived in North America before the Younger Dryas. The black mat sits right on top of their tools and camps, and above the black mat the Clovis culture disappears. The timing fits, the evidence fits. An impact could explain the sudden cooling. The fires would have thrown debris into the atmosphere, blocked the sun, triggered a nuclear winter that lasted centuries. But here's the problem. There's no crater. Impacts leave scars. Big ones. The asteroid that killed the dinosaurs left a crater 110 miles wide. It's still there in Mexico. Easy to find. But from the Younger Dryas? Nothing. Some scientists think it hit the ice sheet. The Laurentide ice sheet covered Canada and the northern United States. It was 2 miles thick. An impact there would have melted billions of tons of ice instantly. The water would have flooded into the Atlantic. No crater because the ice is gone now. That leads to another theory. One that doesn't need an impact at all. The ocean has a conveyor belt. Warm water flows north along the surface. Cold water sinks and flows south along the bottom. This current, the Atlantic meridional overturning circulation, keeps Europe warm. Without it, London would feel like Alaska. The current depends on salt. Salty water is heavy. It sinks. But fresh water is light. It floats. And if you dump enough fresh water into the North Atlantic, the current stops. The ice sheets were melting, had been for thousands of years. Meltwater pooled behind ice dams. Massive lakes held back by walls of ice. Lake Agassiz in North America was bigger than all the Great Lakes combined. Lake Ojibwe, dozens of others, trillions of gallons of fresh water trapped behind ice. Then the dams broke. Geological evidence shows it happened. Suddenly, catastrophically, the lakes drained in weeks, maybe days. All that fresh water poured into the Atlantic at once. The ocean current stopped. Heat stopped flowing north, and Europe froze. The evidence for this is strong. Marine sediments show a massive influx of fresh water right at the start of the Younger Dryas. The timing matches. The mechanism makes sense. Ocean currents have stopped before. They could stop again. But this theory has problems too. It explains Europe, maybe North America. But the Younger Dryas was global. Ice cores from Antarctica show the same cooling. How does a North Atlantic current affect the South Pole? There's another layer to this. Megafauna extinctions. 35 genera of large mammals went extinct in North America at the end of the Ice Age. Mammoths, mastodons, giant ground sloths, saber-toothed cats, short-faced bears, camels, horses, all gone. The extinctions cluster around the Younger Dryas. Some happened just before, some during, almost none after. Something killed them, and it killed them fast. For decades, scientists blamed humans, the overkill hypothesis. We arrived in the Americas around 15,000 years ago, started hunting, drove everything to extinction. But the timing doesn't quite work. Humans and megafauna coexisted for thousands of years before the extinctions. Why would they all die at once? The Younger Dryas offers an answer. Climate whiplash. The animals were adapted to Ice Age conditions, then it warmed. They started to adjust, then it crashed back to cold. Fast. Too fast to adapt twice. The ones that survived the warming couldn't handle the sudden return to ice. The ones adapted to cold had already died off. Humans made it worse. We hunted them while they were stressed, killed them when their populations were already crashing. But the climate delivered the knockout blow. The plant evidence supports this. Pollen cores show forests dying, spruce and pine spreading south, grasslands turning to tundra. The entire ecosystem collapsed, and when the plants died, the animals that depended on them died too. But here's what really gets me: the human evidence. Archaeological sites across North America show abandonment. Clovis points, the distinctive spear points that defined a culture, disappear from the record. The people didn't go extinct, but their way of life did. Something forced them to change. Fast. In Europe, the story is similar. The Alarud period just before the Younger Dryas was warm. Rich. Sites show permanent settlements. Art, complex tools. Then the cold returned. The settlement's empty. The art stops. People went back to moving, back to survival mode. In the Middle East, something different happened. The Nasufian culture was building the first permanent villages, growing wild grains on the edge of agriculture. Then the Younger Dryas hit. The wild grains failed. Food became scarce, so they did something desperate. They started planting, deliberately. Agriculture wasn't a choice, it was survival. The Younger Dryas forced us to farm. There's a site in Turkey called Göbekli Tepe. Massive stone circles built around 9,500 BCE. Right at the end of the Younger Dryas, the stones weigh tons. Moving them required organisation, cooperation, hundreds of people working together. Why build it? Nobody knows. But the timing matters. As the world warmed again, as the crisis ended, humans built monuments, maybe in relief, maybe in memory, maybe to mark the moment we survived. The Younger Dryas lasted 1,200 years. That's 50 generations. If you were born into it, your grandparents were born into it. Their grandparents too. The warm world was myth, story, something the elders talked about but nobody remembered. Then it ended, as suddenly as it began. Around 9,600 BCE, temperatures shot back up, 10 degrees in a decade, maybe faster. The ice retreated, the tundra bloomed, and humans exploded across the planet. Everything we call civilization came after. Agriculture, cities, writing, all of it, built in the 11,000 years since the Younger Dryas ended. We think of that as human history, the whole story, but it's not. It's just the epilogue. The real story is what came before, how we survived the reset, how we made it through the bottleneck, how we adapted when the world tried to kill us. The evidence is everywhere, in ice, in rock, in bones and pollen, and the tools our ancestors left behind. It tells us the planet can change. Fast. Faster than we think possible. And when it does, everything we've built means nothing. We survived last time. Barely. We were hunter-gatherers, mobile, adaptable. Small populations that could move when conditions changed. We're not that anymore. We're locked in place. Billions of us. Dependent on systems that assume stability. The Younger Dryas proved something. Stability is temporary. The warm period we're living in, the Holocene, is an anomaly, a brief window of calm in a violent climate. It won't last forever. It might not last much longer. If you're using this to fall asleep, that's exactly why I make these videos. Maybe subscribe and let me know where you're watching from and what time it is. I always check the comments, and it's fascinating. The Younger Dryas changed everything. Not just the climate, not just the landscape, it changed us. How we lived, how we thought, how we survived. Let's look at what this meant for the whole planet. The cold didn't just hit one place, it hit everywhere, at the same time. That's what the evidence shows, and it's one of the strangest parts of this whole mystery. Lake sediments in Europe tell the same story as ocean cores off Japan. Pollen records from South America match data from Greenland. Cave formations in China show the same pattern as ice sheets in Canada. The whole planet shifted, together, like someone flipped a switch. Let's start in North America. The Clovis people were thriving before this happened. They'd spread across the continent in maybe 500 years, from Alaska to Mexico, from coast to coast. Their distinctive spear points show up everywhere. Beautiful stonework, fluted points designed for hunting megafauna. Then the Younger Dryas hits, and the Clovis culture vanishes. Not gradually, suddenly. Their sites just stop. The distinctive points disappear from the archaeological record. The timeline is stark. Clovis culture ends right when the cold returns, but it's not just humans. The animals disappear too. 35 genera of large mammals go extinct in North America. Mammoths, mastodons, giant ground sloths, saber-toothed cats, short-faced bears, dire wolves, American lions, all gone. Within a few centuries, some scientists say humans hunted them to extinction, but the timing is too perfect. These animals survived hundreds of thousands of years of climate change. They made it through multiple ice ages. Then the Younger Dryas comes and they're gone. Cross the Atlantic. Europe shows the same pattern. The Hamburg culture was flourishing in northern Europe. Reindeer hunters following the herds, then temperatures crash. The Hamburg culture contracts south. Some groups disappear entirely. Forest cover drops by 80% in some regions. The tundra returns. That little Arctic flower, Dryas octopetala, spreads across landscapes that had been warming for 2,000 years. Lake Gurtensee in Switzerland holds a perfect record. Sediment cores show layers of forest pollen, oak, elm, hazel. Then suddenly it stops, replaced by grass and Arctic plants. The transition happens in a single layer. One year you have forest. The next year it's dying. The Mediterranean wasn't spared. Sea surface temperatures dropped 5 to 7 degrees. That might not sound like much, but it was enough. Enough to shift rainfall patterns. Enough to change ocean currents. Enough to stress every ecosystem around that sea. The Levant shows something fascinating. This is the region where agriculture was just beginning. Abu Huraira in Syria, Netiv Hagdud in the Jordan Valley. People were experimenting with cultivating wild grains, building permanent villages. Then the Younger Dryas hits. Some sites get abandoned. Others show a return to hunting and gathering. The experiment with farming pauses. For over 1,000 years, move east to Asia. The monsoons weakened. Cave formations in China called speleothems record this. These are mineral deposits that form from dripping water. The oxygen isotopes in them track rainfall. And right at the start of the Younger Dryas, the monsoons failed. Rainfall dropped 30 to 40% for 1,000 years. Think about what that means. The monsoons feed 1 billion people today. They drive the entire climate system of South and East Asia. When they weakened during the Younger Dryas, crops failed. Rivers dried up. Populations moved or died. The Pacific Islands show changes too. Sea levels stopped rising. They'd been climbing steadily as the ice melted, about 400 feet in 4,000 years. Then the Younger Dryas begins and it stops. The meltwater stops flowing because the melting stops, because the planet got cold again. South America has its own evidence. The Andes show glacier advances. Ice that had been retreating suddenly pushed forward again. Lake Titicaca's water levels dropped. Pollen records show vegetation changes, forests retreating, grasslands expanding. Even Antarctica felt it, though the signal is different there. While the North cooled dramatically, Antarctica actually warmed slightly. This is called the bipolar seesaw. When the North Atlantic cools, heat gets redistributed south. The ice cores from Antarctica show this clearly, a slight warming trend right when Greenland was freezing. But here's what matters. The system is connected. Changes in one place ripple everywhere. The ocean currents link everything together. The atmosphere moves heat around the planet. You can't cool the North Atlantic without affecting the whole world. The Atlantic Meridional Overturning Circulation. That's the technical name for the current system. Warm water flows north on the surface. It cools, gets saltier, sinks, returns south along the ocean floor. This current moves more heat than all the world's rivers combined. It keeps Europe warm. It drives weather patterns across the Atlantic. It affects monsoons in Africa and Asia. And during the Younger Dryas, it weakened. Maybe stopped entirely. The evidence for this is strong. Ocean sediment cores show changes in forum populations. These are tiny shelled creatures. Different species live in different temperature waters, and the species that lived in the North Atlantic during the Younger Dryas are the cold water types. The warm current wasn't reaching that far north. Why did it weaken? The leading theory points to lake Agassiz. This was a massive glacial lake in North America. Bigger than all the Great Lakes combined, it formed from meltwater trapped behind ice dams. And, around the start of the Younger Dryas, something happened. The ice dam broke, or shifted, or melted through, and billions of gallons of fresh water poured into the North Atlantic. Fast. Fresh water doesn't sink like salt water. It's less dense. So all that meltwater floated on top of the ocean, created a lid, stopped the normal sinking that drives the current. The heat conveyor shut down, and without that current bringing warmth north, temperatures crashed. The math works. The timing works. The mechanism makes sense. But some scientists aren't convinced. The amount of water from Lake Agassiz might not have been enough, or it might have drained into the Arctic Ocean instead of the Atlantic. The debate continues. What we know for certain is the global nature of the change. This wasn't a local event. This wasn't one region having a bad millennium. This was planetary. Greenland ice cores show it. Antarctic ice shows it. Ocean sediments show it. Lake records show it. Cave formations show it. Pollen records show it. Glacier positions show it. Every proxy we have for ancient climate points to the same conclusion. The whole Earth system shifted, rapidly, dramatically, simultaneously, and humans were there for all of it, watching their world transform, watching animals disappear, watching forests die, watching rivers freeze that had never frozen before, watching the herds move away, watching food sources vanish. Some populations crashed, some disappeared, some adapted, some moved, some changed everything about how they lived. The archaeological record shows all of these responses. Different groups made different choices, but everyone had to respond, because the planet gave them no choice. The scale is hard to grasp. We're talking about changes that affected every continent except Antarctica, every ocean, every climate zone, from the Arctic to the tropics, from sea level to mountain peaks. Nothing was spared. Nowhere was safe. This is what makes the Younger Dryas so important. It shows us how connected everything is, how a change in one place cascades everywhere, how quickly a stable system can shift to a new state, how vulnerable we are to planetary scale changes. And it shows us something else. It shows us that our ancestors survived. They lived through this. They adapted. They persisted. They found ways to keep going when the world turned against them. That matters, because we're facing planetary changes again. Different causes, different mechanisms, but the same basic challenge. How do you survive when everything changes at once? Our ancestors figured it out. They didn't have technology. They didn't have science. They didn't understand what was happening. But they survived. They adapted. They endured. The evidence of their survival is everywhere. In the tools they left behind. In the sites they occupied. In the fact that we're here at all. We are the descendants of the people who made it through the Younger Dryas. Their resilience is in our DNA. Their adaptability is our inheritance. The planet changed, but humanity continued. That's the story the global evidence tells. That's what matters most. The numbers tell one story. The human cost tells another. We can measure the temperature drop. We can count the extinct species. We can map the abandoned settlements. But those are just data points. Behind each one is a person, a family, a community that had to figure out how to survive. Let's start with the most basic need: food. Before this happened, hunting was predictable. The big animals followed patterns. Mammoths moved with the seasons. Mastodons browsed in forests. Giant ground sloths ate leaves. Horses grazed in herds. You learned their routes. You knew where they'd be. Your grandfather taught your father. Your father taught you. This knowledge kept people alive. Then the animals started dying, not all at once, but steadily, year after year. The herds got smaller, the routes changed, some species just vanished. In North America, 35 types of large mammals went extinct. These were animals that had survived for millions of years. They'd made it through ice ages before, but not this one. Scientists debate why. Some say humans hunted them too hard. Others point to the climate shift. The truth is probably both. The animals were stressed by the cold. Their food sources disappeared. And humans were hunting them. The combination was fatal. For the people doing the hunting, this was disaster. These animals were everything: food, clothing, tools, shelter. A single mammoth could feed a group for weeks. The bones became tools. The hide became clothing and tents. The sinews became thread. Nothing was wasted. When the mammoths died out, people had to change everything. Some groups shifted to smaller game: deer, rabbits, birds. But small animals require different hunting methods, different tools, different strategies, and they provide less food per hunt. You need to catch 10 rabbits to equal the meat from 1 deer. You need 50 deer to equal 1 mammoth. The math didn't work. Populations had to shrink, or move, or starve. Plant foods became more important. But the cold killed many plants. The forests died back. The grasslands shifted. The reliable food sources disappeared. Archaeological sites from this period show the change. Before the cold, you find big game bones: mammoth, bison, horse. After the cold starts, the bones get smaller. More deer, more rabbit, more fish. People were eating whatever they could find. Some sites show something else: evidence of hunger. Bones with cut marks in places that suggest people were getting every scrap of meat, even from parts usually ignored. Skulls cracked open for the brain, long bones split for marrow. Desperation leaves traces. Water was another problem. Not the amount of water. There was plenty of ice. The problem was access. Rivers that used to flow year-round started freezing, springs dried up, lakes got covered in ice too thick to break through. Getting water in winter became dangerous work. You had to melt ice. That requires fire. Fire needs fuel. And fuel was getting scarce. Trees died in the cold, the forest retreated. In some places, wood became rare. People burned bones, dried dung, anything that would catch fire. Because without fire, you died. Simple as that. Fire meant warmth. Fire meant cooked food. Fire meant safety from predators. Fire meant light. Fire meant community. Humans need fire, especially in the cold. Sites from this period show changes in hearth construction. People built better fires, more efficient. They dug fire pits deeper, lined them with stones to hold heat, created windbreaks. Every bit of fuel had to count. Shelter became critical. Before the cold, some groups lived in simple structures, light frames covered with hides, easy to move, easy to rebuild. That didn't work anymore. The cold demanded better shelter. People dug into hillsides, built thick walls, created smaller spaces that were easier to heat. Some groups started using mammoth bones as building materials. The big leg bones made supports. Skulls and ribs formed walls. Hides stretched over the frame. These weren't temporary camps. These were engineered structures, built to last, built to survive winter. The effort required was enormous, but necessary. Clothing had to change too. Thin hides weren't enough. People needed layers, insulation, protection from wind. Archaeological evidence shows more complex clothing, tailored garments, stitched seams, fitted boots. These things take time to make. They require skill, but they mean survival. Some sites show needles, bone needles with eyes for thread. These appear more frequently during the cold period. People were sewing, creating fitted clothes, using every scrap of hide efficiently. Social structures probably shifted. In good times, groups could spread out. Family bands could live independently. But in hard times, you need numbers, more hunters, more gatherers, more hands to build shelter, more eyes to watch for danger. Larger groups mean new problems, more mouths to feed, more personalities to manage, more potential for conflict, but they also mean better odds of survival. Shared knowledge, shared resources, shared labour. The archaeological record shows changes in settlement patterns. Sites get larger, more people living together, but they're also more carefully chosen, near water, near shelter, near whatever food sources remained. Trade networks probably became vital. If your region lost all the big game, maybe another region still had some. If your area ran out of good stone for tools, maybe you could trade for it. Moving goods meant moving survival. We see evidence of long-distance trade during this period, shells from the coast showing up hundreds of miles inland, stone tools made from rock that only exists in specific places. These things travelled, which means people were connected, helping each other, trading, surviving together. Children born during this time knew nothing else. For them, the cold was normal, the scarcity was normal, the constant struggle was just life. Their parents might have told stories about better times, about forests and plenty, but those were just stories. Imagine being a parent then, trying to keep your children alive, watching them go hungry, knowing the world used to be easier, knowing it might never be easy again. That's not abstract. That's real. That happened. Some groups made it. They adapted. They survived. We know because we're here. Our ancestors were the ones who figured it out, who made the right choices, who got lucky, who endured. Other groups didn't make it. Sites show abandonment. No more layers of occupation, no more tools, no more fires, just empty. People either moved or died. The archaeological record can't always tell which. Population estimates for this period are rough, but most scientists agree numbers dropped. Maybe by half, maybe more in some regions. Humans nearly went extinct several times in our history. The Younger Dryas might have been one of those times. The genetic evidence backs this up. Studies of human DNA show bottlenecks. moments when diversity dropped, when populations crashed. Some of those bottlenecks line up with the Younger Dryas. The survivors passed on their genes. Everyone else disappeared. This wasn't noble. This wasn't heroic. This was desperate survival. People doing whatever it took, making impossible choices, living with those choices. The Younger Dryas lasted 1,200 years. That's 40 generations. 40 generations of cold, of scarcity, of struggle. Nobody alive remembered the before times. Nobody could imagine the after. But the after came. The ice melted, the cold ended, the world warmed again, and the survivors emerged changed. They'd learned things, developed new skills, created new tools, built new social structures. Some scientists think agriculture emerged partly because of the Younger Dryas. When the cold ended, people remembered hunger. They didn't want to depend only on wild animals and plants, so they started controlling their food sources, planting seeds, keeping animals, creating surplus, building security. Maybe, we can't know for sure, but the timing fits. Agriculture appears right after the Younger Dryas ends, in multiple places, almost like people everywhere decided they needed a new way to survive. The human cost of the Younger Dryas was enormous, but the human response was remarkable. People adapted, they survived, they rebuilt, they created new ways of living, new technologies, new societies. We carry that resilience. We're the descendants of the people who made it through. Their determination lives in us, their creativity, their refusal to give up. That's our inheritance. That matters. Target: 1,750 words, approximately 2,333 tokens for content. Style guide and context: approximately 15,000 tokens. Reserve for response: approximately 3,000 tokens. Status: well within 200,000 budget. Humans struggled, but they weren't the only ones. The megafauna were dying too, and their deaths tell us something important about what was happening, about the scale of it, about how fast everything changed. Let's talk about what was lost. Before the cold returned, North America had animals that seem impossible now. Creatures so large they dwarf anything alive today except elephants. The Columbian mammoth stood 14 feet at the shoulder, weighed 10 tons, its tusks curved 16 feet long. These animals moved in herds across grasslands that stretched from Canada to Mexico. They ate 800 pounds of vegetation every day. They shaped entire ecosystems just by existing. Giant ground sloths were the size of modern elephants. They walked on their knuckles, reached up to strip leaves from trees 20 feet high. Some species weighed 4 tons. They'd been around for 30 million years. Mastodons looked like mammoths but weren't. They browsed in forests, ate twigs and leaves. Their teeth were different, built for crushing, not grinding. They lived in family groups, raised their young for years. Sound familiar? They were more like us than we want to admit. Short-faced bears stood 12 feet tall on their hind legs. They could run 40 miles per hour. Nothing could escape them. Nothing could fight them. They were the apex predator of an entire continent. Dire wolves hunted in packs, larger than modern wolves, stronger jaws, built for taking down prey that weighed tons. They worked together, coordinated, survived by cooperation. American lions were bigger than African lions today. Saber-toothed cats had 7-inch fangs. Giant beavers weighed 200 pounds. Camels roamed the plains. Yes, camels. They evolved in North America before spreading to Asia and Africa. This wasn't ancient history. This was 12,000 years ago. These animals walked the same ground we walk now. Then, the cold came back. Within a few hundred years they were gone, all of them. 35 genera of large mammals extinct. Not just in North America, everywhere. South America lost even more. Giant armadillos the size of cars. Toxodon, which looked like a rhino crossed with a hippo. Glyptodonts with spiked tails like medieval weapons. Macrauchenia, which had a trunk like an elephant but was related to horses. Europe lost woolly rhinos, cave bears, giant elk with antlers 12 feet across. Australia had already lost its megafauna earlier. Giant wombats, marsupial lions, kangaroos 10 feet tall. Scientists call this the Quaternary extinction event. It's the most recent mass extinction, and we're still arguing about what caused it. Some say humans did it. The overkill hypothesis. People spread across continents and hunted everything to death. We were too good at killing, too efficient. The animals had no fear of us. We wiped them out. There's evidence for this. Wherever humans show up, extinctions follow. Australia lost its megafauna 40,000 years ago, right when humans arrived. Madagascar lost its giant lemurs and elephant birds 1,500 years ago, right when humans arrived. New Zealand lost its mouse 600 years ago. Same pattern. But the timing doesn't quite work for the Younger Dryas extinctions. Humans had been in North America for at least 15,000 years, maybe longer. Why did it take so long to kill everything? Why did the extinctions happen suddenly, right when the climate crashed? Other scientists point to the climate. The cold killed them. Their food disappeared. The ecosystems collapsed. They couldn't adapt fast enough. There's evidence for this too. Pollen records show massive vegetation changes. The plants these animals ate vanished. Forests died. Grassland shifted. The landscape transformed. But here's the problem. These animals had survived climate changes before. Many times they'd lived through multiple ice ages. Warming periods, cooling periods. They'd adapted, migrated, survived. So why not this time? Maybe it was both. The animals were already stressed by human hunting. Then the climate crashed. The combination was too much. They couldn't handle both pressures at once. Or maybe something else happened. Something we haven't figured out yet. Look at the mammoths. We have their DNA now. Scientists can sequence their genes, study their populations, track their decline. The genetic evidence shows something strange. Mammoth populations were healthy until the very end. Good genetic diversity. No signs of inbreeding. No indication they were struggling. Then suddenly, they're gone. It wasn't a slow decline. It was a crash. We even know when the last mammoths died. A small population survived on Wrangel Island in the Arctic Ocean until 4,000 years ago. The pyramids were already ancient when these mammoths went extinct. That's how recent this is. But the mainland populations, they disappeared. During the Younger Dryas, along with everything else, the extinction pattern is weird. Small animals mostly survived. Birds made it through. Fish were fine. Even some large animals survived. Bison, moose, elk, caribou. Why them and not the others? Nobody has a good answer. The survivors don't follow an obvious pattern. Some lived in cold climates, some didn't. Some were grazers, some were browsers, some were predators, some were prey. What separated the survivors from the extinct? We don't know. Here's what we do know. The extinctions changed everything. When the mammoths died, the grasslands changed. Mammoths kept forests from spreading. They knocked down trees, ate saplings. Their grazing maintained open grasslands. Without them, forests spread. The landscape transformed. When the giant herbivores died, the predators died too. No prey means no predators. The whole food chain collapsed from the bottom up. When the megafauna died, humans lost their primary food source. This forced changes in how people lived, what they ate, how they hunted, where they settled. Some scientists think the extinctions helped push humans toward agriculture. When you can't rely on hunting big game anymore, you start looking for other options. You start controlling your food sources, planting seeds, keeping animals. The timing fits. Agriculture appears right after the extinctions, in multiple places. Almost like people everywhere reach the same conclusion at the same time. We needed a new way to survive. But there's something else the extinctions tell us. Something about how fragile these systems are. These animals had been around for millions of years. They'd survived everything Earth threw at them. They were successful, adapted, thriving. Then in a few hundred years, they were gone. It didn't take long. That's the scary part. A few bad centuries and millions of years of evolution just ended. We tend to think of extinction as a slow process. Populations declining. Has dropped below a critical threshold. There aren't enough individuals left to recover. The genetics are too limited. The ecosystem has already shifted. Then it's just a matter of time. The Younger Dryas extinctions happened in maybe 500 years. That's fast in geological time, but it's slow in human time. That's 10 generations, 20. Your great-great-grandchildren might see the last mammoth, but they wouldn't remember when mammoths were common. The change would feel normal to them. This is just how the world is, always has been. The stories about vast herds and giant animals would seem like myths, exaggerations, the old days that probably weren't as good as Grandpa says. But they were real, and they were lost. We're living in the aftermath of this extinction. The world we know as the world that survived. We think it's normal, but it's not. It's depleted, emptied out, missing most of its largest animals. Imagine if the extinctions hadn't happened. Imagine mammoths still roaming, giant sloths in the forests, dire wolves in the mountains. How different would human civilization look? How would we have developed with these creatures still around? We'll never know. That timeline ended 12,000 years ago. What we have instead is a world that's still recovering, still adjusting to the absence of animals that shaped ecosystems for millions of years. The grasslands are different, the forests are different, the whole balance shifted. And it shifted because of the Younger Dryas, because the climate crashed, because something happened that we still don't fully understand. The megafauna couldn't adapt fast enough. They couldn't survive the combination of climate change and human pressure. They died, and their deaths changed the world. We survived, but we were changed too, forced to adapt, to find new ways to live, to create new technologies, to build new societies. The extinctions shaped us as much as they shaped the landscape. We carry that loss with us, even if we don't realize it. The world is quieter now, emptier, less diverse. We lost something we can never get back, but we learned something too. We learned that nothing is permanent, that successful species can vanish, that the world can change faster than we expect. That's a lesson worth remembering. So what caused all this? That's where the mystery really begins. We've seen what happened. Temperatures crashed. Animals died. People struggled. But we still don't know why. Scientists have been arguing about this for decades. And the more evidence we find, the stranger it gets. Let's look at the theories. The oldest explanation is simple. The ice sheets melted. All that fresh water poured into the North Atlantic. This disrupted ocean currents, specifically something called the Atlantic Meridional Overturning Circulation. Here's how it works. Warm water flows north from the tropics. It carries heat toward Europe and North America. When it reaches the Arctic, it cools down. Cold water is denser. It sinks, then flows back south along the ocean floor. This current moves heat around the planet. It keeps Europe warm. It moderates climate across the northern hemisphere. It's been running for millions of years. But fresh water changes everything. Fresh water is less dense than salt water. It doesn't sink as easily. If you dump enough fresh water into the North Atlantic, the current slows down. maybe stops, and that's exactly what happened before. During earlier cold periods, we have evidence of this. Lake Agassiz was a massive glacial lake in North America, bigger than all the Great Lakes combined. It was held back by ice dams. Sometimes those dams broke. Billions of gallons of fresh water rushed into the ocean, and the climate cooled. We can see this pattern in the geological record. It happened multiple times during the last ice age, so maybe it happened again, right at the start of the Younger Dryas. The ice dam broke, the lake drained, the current shut down, the climate crashed. This theory makes sense. It fits the evidence. It explains the rapid cooling. It explains why the Northern Hemisphere was hit hardest. But there's a problem. The timing doesn't quite work. Lake Agassiz did drain. But the evidence suggests it drained east into the Atlantic, and this might have happened after the cooling started, not before. Some scientists say the lake drained north instead, into the Arctic Ocean, through the Mackenzie River. This would still disrupt the current, still cause cooling, and the timing fits better. Others point to different sources: meltwater from the Scandinavian ice sheet, or the Laurentide ice sheet. There was a lot of melting happening, a lot of fresh water entering the ocean. The ocean current theory is still the leading explanation. Most scientists accept some version of it, but the details keep shifting. New evidence keeps complicating the picture. And then there's the other theory, the one that sounds like science fiction. What if something hit us? In 2007, a group of scientists proposed something radical. They said a comet exploded over North America, right at the start of the Younger Dryas. The impact caused massive fires, threw debris into the atmosphere, blocked out the sun, triggered the cooling. They called it the Younger Dryas Impact Hypothesis, and it created a firestorm in the scientific community. Here's their evidence. That layer of black carbon we talked about earlier, the soot from massive fires, it shows up right at the boundary, across multiple continents. Something burned, something huge. Then there are those rare elements, platinum, iridium. They spike at the same level. These elements are common in asteroids and comets, rare on Earth's surface. Finding them concentrated in one layer suggests extraterrestrial material. There's more. Nanodiamonds. Tiny diamonds that form under extreme pressure and heat. The kind you get from impacts. They show up in the boundary layer, in multiple locations. Magnetic spherules. Little balls of melted rock with magnetic properties. They look like they formed from material heated to extreme temperatures, then cooled rapidly, like from an impact. And here's the kicker. At a site called Abu Huraira in Syria, they found glass, melted glass mixed with the sediment. Analysis showed it formed at temperatures above 2,200 degrees Celsius, hot enough to melt sand instantly. The scientists say only two things can create that kind of heat: a nuclear explosion or a cosmic impact. The impact theory would explain a lot: the sudden cooling, the fires, the extinctions, the collapse of human populations, all from one catastrophic event. But most scientists don't buy it. They found problems with almost every piece of evidence. The platinum spike. Some studies can't replicate it. Other studies find platinum in layers that have nothing to do with impacts. Maybe it's not as rare as we thought. Maybe contamination explains it. The nanodiamonds, they might form naturally, from wildfires, from geological processes. Finding them doesn't necessarily mean impact. The magnetic spherules, they could be industrial contamination, or natural particles, or micrometeorites that fall constantly. Nothing special about them. The black carbon layer, wildfires can explain it. Climate change caused droughts. Droughts caused fires. Fires produced soot. No impact needed. And here's the biggest problem. Where's the crater? A comet big enough to cause global effects would leave a crater. A big one. We haven't found it. The impact theory supporters say it exploded in the air, an airburst, like the Tunguska event in 1908. A meteor exploded over Siberia, flattened 2,000 square kilometers of forest, but left no crater. Maybe the Younger Dryas impact was like that, but bigger, much bigger, big enough to affect the whole planet. Or maybe it hit the ice sheet. The Laurentide ice sheet was 2 miles thick. An impact there might not leave a crater we could find. The ice would absorb it, then melt away over thousands of years, taking the evidence with it. It's possible. But most scientists want more proof. Extraordinary claims need extraordinary evidence, and the evidence for an impact is contested, debated, not conclusive. So where does that leave us with two main theories? Both have problems, both have supporters. The ocean current theory makes sense. It's based on processes we understand. It's happened before. But the timing is fuzzy. The details don't quite line up. The impact theory is dramatic. It would explain the sudden change, but the evidence is controversial. Most scientists don't accept it. Maybe it's both. Maybe an impact triggered the ocean current shutdown. The fires and debris caused initial cooling. This led to rapid ice sheet melting. The meltwater disrupted the currents. The cooling continued. Or maybe it's neither. Maybe something else happened. Something we haven't thought of yet. That's the frustrating thing about ancient mysteries. We're looking at events from 12,000 years ago. The evidence is fragmentary. Interpretation is difficult. New discoveries change everything. 20 years ago, most scientists had never heard of the impact hypothesis. Now it's a major debate. What will we know in 20 more years? The truth is, we might never know for certain. The evidence might be too degraded, too scattered, too ambiguous. We're trying to reconstruct a disaster from 12,000 years ago. With incomplete data and competing interpretations. But here's what we can say. Something happened. Something big enough to reverse the warming. Something fast enough to catch the whole planet off guard. Something powerful enough to change the course of human history. Whether it was ocean currents or cosmic impact or both or something else entirely, the result was the same. The world changed. Suddenly, dramatically, irreversibly, and people had to adapt, had to find new ways to survive, had to create new technologies, new strategies, new societies. The mystery of what caused it matters, but maybe what matters more is what happened next, how humans responded, how we survived, how we changed, because we did survive, against incredible odds. Through 1,000 years of cold, through extinctions and starvation and collapse, we made it through. And on the other side, we were different. We'd learned something about resilience, about adaptation, about what humans can endure. The Younger Dryas nearly ended us. Instead, it transformed us, pushed us toward agriculture, toward civilization, toward the world we know today. We carry that transformation with us, even now, even if we don't realize it. We're the descendants of the survivors, the ones who adapted, who changed, who refused to give up. That's worth remembering. When things seem impossible, when change feels overwhelming, when the future looks uncertain, we've been through worse. We've survived worse. We'll survive again. Let's dig into the water theory. Meltwater. It sounds simple, almost boring, but it's one of the biggest forces shaping our world. Think of those giant ice sheets at the end of the last ice age, miles thick, covering Canada, northern Europe, parts of Asia. These weren't just piles of frozen water, they were like slow-moving mountains. As the world warmed, these sheets started to melt. Not slowly either. Some years, the ice retreated miles in a single summer. All the water had to go somewhere. Some of it soaked into the ground, making lakes and rivers, but most of it ran off into the sea. Now, oceans don't just sit there. They're like giant conveyor belts. Warm water moves north along the surface, cools down, sinks, and then flows back south deep below. This keeps places like Europe much warmer than they should be. Without it, London would feel like northern Canada. So, what happens if you dump a ton of cold, fresh water into that system? It's like dumping syrup into a coffee maker. Everything clogs up. The warm water can't sink like it used to. The conveyor belt slows down or even stops. Suddenly, places that used to get warm breezes from the tropics start to freeze. The pattern breaks. Weather changes. Storms hit new places. Rain falls where it didn't before. Droughts start in other regions. It's chaos. This is the backbone of the meltwater theory. The idea is that one or more giant lakes trapped behind ice dams suddenly burst. Imagine a lake bigger than all the Great Lakes combined. One day the dam goes, billions of tons of water flood into the North Atlantic. Geologists have found old shorelines and river channels that don't match today's maps. They've found sand and mud in places only a giant flood could reach. They've even traced the path of these ancient floods from Canada all the way to the ocean. One of the biggest suspects, Lake Agassiz. It covered huge parts of North America. For thousands of years it sat behind an ice wall getting bigger and deeper. Then the wall failed. The water raced north, east, and even south, depending on how the ice shifted. Every time it drained, the ocean changed. Salty water mixed with fresh. Layers of warm and cold shifted. Scientists call this stratification. But really, it's just the ocean getting confused. The system relies on salt and temperature to move water around. Mess with that, and you mess with the planet's thermostat. Let's slow down and picture what this meant for people living back then. Imagine a river that's always gentle. One day the banks burst. Torrents of icy water pour through the valley. Trees rip out of the ground. Animals scatter. Anything in the way gets swept. Downstream. The flood doesn't stop for days, maybe weeks. When it's over, the land is different. New lakes, new swamps, new paths for rivers. But the real impact is far away. Where that water hits the sea, it's not just a local disaster, it's global. Within years or even months, the weather changes everywhere. Places that were warming up suddenly freeze again. So why do scientists think this is what happened? It comes down to layers. Layers of mud, sand, pollen, and even the chemistry of the ocean itself. In places like the North Atlantic, ocean cores show sudden changes right when the climate snapped cold. The shells of tiny sea creatures tell us the water got fresher. That only happens if a lot of fresh water poured in quickly. It's not just the Atlantic. The same sudden changes show up in lakes and rivers across Europe and Asia. Caves in China record a shift in rainfall. South American lakes get saltier as water patterns switch. The fingerprints are everywhere, but here's what really seals the deal for the meltwater theory. The timing lines up, almost. Around the time the world turned cold, there's evidence for huge floods. Some happened just before, some just after, but all within a few hundred years. In geological terms, that's like the blink of an eye. And the physics works. If you pour enough fresh water into the North Atlantic, the conveyor belt shuts down. Temperatures drop. Sea ice spreads. More sunlight bounces off the ice, making things even colder. It's a feedback loop. Now, the details get messy. Some researchers say the big flood came a little too late. Others argue it was right on time. Some think there were several smaller floods instead of one giant one. Every new study adds a twist. But almost everyone agrees that meltwater played a role. Let's get even more specific. There's a place called the Mackenzie River. It runs from Lake Agassiz up to the Arctic Ocean. Some geologists think the lake drained this way. instead of east into the Atlantic. If that's true, the fresh water would still end up in the sea. It would still mess with ocean currents. Some computer models show this could have triggered cold snaps almost as strong as dumping the water straight into the Atlantic. Other scientists look at Europe. The ice sheets there were melting too. Norway, Sweden, Scotland, all had rivers of meltwater pouring out. The North Sea filled with fresh water. This could have added to the chaos, making the system even more unstable. There's another twist. Some researchers think the floods happened over and over, not just once. Each time the ice melted a little and a lake got big enough, another flood hit. The climate would wobble, cool down, then warm up, then cool again. It's like someone flicking a light switch on and off. But every version of the theory comes back to one main idea. Meltwater changed the rules. It didn't just add water to the ocean, it rewrote the script for how heat moves around the planet. Think about the animals living through this. Herds of caribou and bison, used to certain migration paths, suddenly find rivers too wide to cross. Forests die back, grasslands turn to marsh, the food web collapses. Even if the animals survive the cold, the land they depend on is different. And for people, everything gets harder. Hunters can't follow the same trails. Plants don't grow in the same places. Fish migrate differently. The world you knew as a child isn't the world you live in as an adult. Let's zoom out again. The last ice age ended with a series of dramatic pulses. Every time the ice melted fast, the world changed. Sometimes it warmed, sometimes it froze again. The pattern is messy, but it's clear that water, especially fresh water, has the power to flip the climate almost overnight. So why does fresh water matter so much? Salt water is heavy, it wants to sink. Fresh water is lighter, it floats on top. The ocean's conveyor belt needs heavy salty water to drive the system. Too much fresh water, and the engine stalls. Picture a giant water park ride. The water flows up and down, twists and turns, always moving. Now imagine someone dumps a tanker truck of syrup into the pool. Suddenly nothing works like it's supposed to. The ride slows or stops. That's what happened with the North Atlantic. The system stalled. Heat stopped moving north. Ice spread south. Places that should have been warming up froze again. Some scientists have even looked at ancient tree rings. In Ireland and Scandinavia, trees stopped growing for years at a time. The seasons got shorter. Summers were cold and wet. Winters were brutal. The trees don't lie. They record every bad year in their rings. Caves tell the story too. Stalactites and stalagmites grow faster when there's rain, slower when it's dry. In some caves, growth almost stops for centuries. The water stopped flowing. The land dried out or froze. Even the chemistry of the air changed. Trapped bubbles in ancient ice show levels of carbon dioxide and methane dropping fast. These gases act like a blanket trapping heat. When they drop, the world cools even more. And all of this ties back to meltwater. Not just a little, but massive floods. Water moving faster and in bigger amounts than anything humans have ever seen. Here's where things get philosophical. We live in a world where water feels safe. It falls as rain, fills rivers, sits quietly in lakes. But water is one of the most powerful forces on Earth. It shapes continents. It can end worlds, at least the worlds people are used to. So, what does this theory mean for us today? It's a warning, but also a clue. Our climate is balanced on a knife edge. Change one thing, like how much fresh water enters the ocean, and the whole system can shift. That's not just ancient history. Modern scientists worry about the same thing happening again. Greenland is melting fast right now if water enters the North Atlantic. The conveyor belt could slow down again. Some computer models even suggest this could start within our lifetimes. But 12,000 years ago, People didn't know any of this. They just saw the world get colder. They watched the animals disappear. They moved, adapted, or died. And when the climate finally shifted back, everything was different. Let's talk about how certain we are. The meltwater theory is strong because it fits with how the planet works. We know floods happened. We know ocean currents can change the weather. We can see the scars left behind, in river valleys, in ocean mud, in the chemistry of ancient ice. But there are still puzzles. Why did the cold snap start so suddenly? Why did it last so long? Why did it end just as fast? Some researchers think there must be more to the story. Maybe another trigger. Maybe a chain reaction. And there's another problem. Not all the evidence lines up perfectly. Some floods happened before. The cold period. Some after. Maybe the records we have aren't complete. Maybe smaller floods combine to tip the balance. Or maybe we're missing something. Maybe there's a piece of the puzzle we haven't found yet. Something hidden deep under the ocean, or under layers of rock and ice. But here's what matters. Water shapes our world in ways we're only beginning to understand. It can end an age, it can start a new one, and it can do it almost overnight. The meltwater theory isn't just about floods and ice. It's about how fragile everything is, how quickly the world can flip from one state to another. How a single event can ripple out, changing everything. It's worth remembering that the people who lived through all this didn't have the science. They just had their eyes, their memories, their stories. Some survived by moving, others by inventing new ways to live. Their resilience is written in our genes. So next time you see a quiet lake or a slow river, think river about this. That same water, given enough time and the right push, can change the world. It has before, it might again. And while the meltwater theory explains a lot, there are still questions, still gaps, still mysteries left to solve. Because as much as water can change the world, sometimes it's not the only thing at work. Some scientists think something else happened, something from space. Water theory is grounded, but space theory is more dramatic and more controversial. Let's get into it. Imagine you're living 12,800 years ago. The world is warming, slowly waking up from a long freeze. Animals are everywhere. People are starting to settle. Then, out of nowhere, the climate crashes. The cold comes back fast. Crops fail. Herds vanish. Whole cultures disappear. What could cause something this sudden? Some scientists started thinking bigger, much bigger. They began to look up, not down. Maybe the answer was in the sky. Here's the wild idea. Cosmic impact. Something from space, like a comet or asteroid, slammed into Earth. Not a dinosaur killer, but still huge. Big enough to shake the planet's climate. Even the thought sounds like a movie plot. But there's real evidence worth looking at. So let's break down what led people to this idea. First, the timing. The cold snap starts almost overnight. Not over centuries or even decades. In some places, the change is so fast you can see it in a single layer of mud or ice. That's not how most climate shifts work. Usually it's slow. But this, it's abrupt. Next, the weird stuff found in the ground. In several places across North America and Europe, scientists found a thin layer of black. It's not dirt. It's not just burned wood. It's a mix of carbon, melted minerals, and tiny glass beads called microspherules. These show up right at the start of the cold period. Why does this matter? Because these materials don't form just anywhere. They need intense heat. We're talking thousands of degrees, way hotter than normal forest fires, the kind of heat you get from something slamming into Earth at 20,000 miles an hour. Along with the black layer, there's another clue: strange metals. In ice and in the soil, researchers found high levels of platinum, iridium, and even small diamonds. These are rare on the surface, but they're common in space rocks. Put these clues together and you get a picture. Something fiery, something violent. Maybe a comet or asteroid broke up in the air like what happened over Siberia in 1908. Only this time it was even bigger. But how big are we talking? Not a dinosaur-ending rock, thankfully. Those are miles wide. This would be smaller, maybe half a mile across. Still, the energy is mind-blowing. If a space rock that size hit, it would release more power than every nuclear bomb on Earth going off at once. So, what would that look like? For people living then, it would be the worst day in history. The sky lights up, there's a flash, then a shockwave. If it hit ice, massive sheets would explode into steam. Fires would race across grasslands. Dust and soot would rise into the sky. The sun would dim for months, maybe years. The plants die. Animals starve. People have to move or die trying. The climate doesn't just cool, it crashes. Why do some scientists think it hit the ice, not land? Here's why. The evidence of melted minerals and glass beads is mostly found near old ice sheets. If a comet hit solid ground, you'd expect to find a classic crater, like Meteor Crater in Arizona. But there's no obvious giant hole from this time. But ice is different. If you hit a mile-thick glacier, most of the energy goes into melting and vaporizing ice. The impact would leave less of a mark. The crater might be hidden or even erased as the ice melted away in the centuries after. Here's another angle. The black layer isn't just found in one place. It shows up in a dozen spots. Across North America, parts of Europe, and even the Middle East. The same kind of soot, the same weird glass, the same rare metals. All showing up right at the start of the Cold Era. That looks like a global event, or at least something that touched a huge part of the world. Local fires can't do that. Volcanoes leave different clues. Ash, not glass beads or platinum. Some of the most interesting finds come from South Carolina and Pennsylvania in the United States. In old riverbeds, scientists found tiny spheres of iron and carbon. Under the microscope, they look like little beads of melted metal. They only form under extreme heat and pressure. Not the kind you get from a simple wildfire. And the diamonds. These aren't the kind you find in jewellery. They're nanodiamonds, tiny crystals that form when carbon is crushed and heated in a split second. You see them in meteorites and at nuclear test sites. Finding them here, in the same black layer, is a big deal. Now, let's talk about the people who lived through this. There's a pattern that's hard to ignore. Cultures in North America vanish right at the time the black layer appears. Same with some groups in Europe. The animals go too. Mammoths, mastodons, saber-toothed cats, all disappear within a few centuries of the event. The cosmic impact theory tries to explain why. If you set off fires across 2 continents, block out the sun, freeze the world, and destroy food sources, it's no wonder people and animals disappear. But there's more. Scientists have found ancient lake beds in the western United States with odd chemical fingerprints. There's a sudden jump in certain elements, like nickel and platinum, that match what you'd find in a comet, not in regular rock. The timing matches the start of the cold snap. In Europe, peat bogs and lake sediments show spikes in iridium, another rare metal from space. It's not everywhere, but the spots line up with the timing of the black layer. And in Greenland, buried deep in the ice, there's a sudden surge of platinum. It's hundreds of times higher than normal. This spike shows up right when the temperature collapses. It's not just dirt and ice. Ancient bones tell a story too. In some mammoth tusks and bison bones from Alaska, there are odd scars and cracks. Some researchers think these might be from sudden intense heat, maybe even from a shockwave or blast. It's not proof, but it's strange. So, what does the cosmic impact theory actually say? Here's the basic idea. Around 10,800 BCE, a comet or asteroid broke up as it entered Earth's atmosphere. Some pieces exploded in the air like the Tunguska event in 1908. Others may have hit the ice sheets in North America. This set off wildfires across huge areas. The impact vaporized ice, throwing steam and dust high into the sky. Soot and debris blocked out sunlight. The planet cooled fast. Oceans and weather patterns went haywire. The result was a deep, sudden freeze that lasted for centuries. It's a chain reaction. One big event triggers a cascade of disasters, fires, then cold, then starvation. But here's where the theory gets tricky. There's no giant smoking gun, no obvious crater, so critics push back. They say the black layer could be from regular wildfires, maybe even from volcanoes. But the people who support the space theory point to the weird mix of glass, metals and diamonds. You don't get all of those from normal fires, and the timing is almost too perfect. The black layer, the rare metals, the sudden drop in temperature, they all match up. Still, not everyone is convinced. Some scientists say the evidence is patchy. The black layer doesn't show up everywhere. Some spots have the glass beads and metals, others don't. Maybe the materials travelled on winds. Maybe they settled only in certain places. Or maybe there was more than one event. Another argument is about timing. Some data suggest the layer appears a bit before the cold snap in some places, a bit after in others. Is that just a problem with dating the layers, or does it mean something else happened? And then there's the question of size. Could a comet half a mile wide really trigger 1,000 years of cold? Some climate models say yes, others say it's not enough. But what about the stories people told? Some researchers look at old myths from Native American and Siberian cultures. They talk about fire falling from the sky, of darkness, of a time when the world almost ended. Is this just coincidence, or are these distant memories of a real event? Nobody knows for sure. It's hard to prove a comet hit when the evidence is buried under thousands of years of mud, ice, and water. But the clues keep piling up. Let's zoom out for a second. Cosmic impacts aren't just science fiction. They happen. A big rock wiped out the dinosaurs 66 million years ago. In 1908, a small asteroid exploded over Siberia. It flattened 80 million trees in seconds. People heard the blast 1,000 miles away. In 2013, a much smaller rock exploded over Russia. The shockwave blew out windows and injured over 1,000 people. These things don't just happen in the movies, so if a comet hit 12,000 years ago, it wouldn't be the first time space has changed life on Earth. It wouldn't be the last either. The cosmic impact theory is dramatic, but it fits some of the facts. The sudden cold, the black layer, the rare metals, the vanishing animals and cultures. It's a simple story in some ways, but the details are messy. Some researchers are looking for more proof. They're digging in places where the ice sheets used to be, hoping to find a hidden crater. Some think there might be one under the Hiawatha Glacier in Greenland. Radar scans show a round depression almost 20 miles wide, but it's buried under half a mile of ice. If that's the crater, it would fit the timeline. But the dating isn't certain. It might be older, it might be newer, the jury is still out. Other scientists use computer models to test what would happen if a comet hit the ice. The models show that enough dust, soot and water vapour could block out the sun and cool the planet. But real life is always more complicated than a simulation. There are other angles too. Some researchers point to a type of stone called melt glass. It's found in the black layer in a few places. It forms when sand and rock are heated to thousands of degrees, then cool almost instantly. You see it at nuclear test sites. Finding it in ancient soil is strange. Others point to the sudden spread of wildfires. Charcoal from burned forests shows up in lake beds across North America. The timing matches the event. but some believe regular climate change could have set off the fires, not a rock from space. So, what's the truth? Honestly, nobody can say for sure. The cosmic impact idea is bold. It explains a lot, but the evidence is scattered. The debate gets heated. Some scientists say it's settled. Others say it's just a story. But the idea sticks with people. Maybe it's because it's dramatic. Maybe it's because deep down, we know space is unpredictable. Rocks do fall from the sky. Sometimes they change everything. Here's what matters for this story. For a long time, people thought climate could only change slowly. But the layers in the ground, the ancient soot, the strange metals, they all hint at a world that can flip in an instant. Not just from water or ice, but from something far above our heads. If a comet really did hit the ice, it shows how fragile life is. One bad day, and the world you know is gone. People and animals have to start over. Some don't make it. But it also shows something else. The survivors adapted. They changed the way they lived. They shaped the world that came after. And even if the impact theory turns out to be wrong, it's a good reminder. Space is part of our story. It's not just up there. Sometimes it comes down here. And when it does, nothing is ever the same. Now, as wild as the space theory sounds, there's another possibility. Maybe Earth did this to itself. All right, so maybe water played a role. Maybe something from space did too. But there's one more angle to consider. What if the planet itself set the trap? Not the oceans, not the sky, the ground right under our feet. Let's talk about Earth systems, the hidden engines that make our world work. Volcanoes, shifting plates, and the cycles deep underground that most of us never think about. Sometimes, these forces shape everything above without warning. Here's the thing. Earth isn't just a passive stage for history. It's active. It moves. It changes. Sometimes it flips the script. So, what could the planet have done to spark such a sudden freeze? Let's start with volcanoes. They're the wild cards of climate. When a big one blows, it can throw ash and gases high into the sky. These can block sunlight, cool the planet, and mess with weather for years. We've seen this happen in recent history. In 1815, Mount Tambora erupted in Indonesia. It was so powerful that the ash spread around the world. The next year, 1816, became known as the year without a summer. Crops failed, people starved, frosts hit in June and July. That was just one volcano. So, what about the time we're talking about? Did a giant eruption set off the cold snap? Scientists have hunted for signs, ash layers, volcanic glass, sulfur in ice cores. There are some hints. A few spots show traces of ash from eruptions, but nothing that matches the scale or timing of the big freeze. It's possible a series of smaller eruptions helped tip the balance. Multiple volcanoes going off in a short window could add up. Maybe they work together with other factors, blocking the sun, cooling the air, and setting off a chain reaction. But there's no smoking gun, volcano, not one that lines up perfectly with a sharp temperature drop. Some think the evidence is just missing, wiped away by time or buried deep below ancient lakes and forests. Others wonder about gas. Volcanoes don't just throw ash. They pump out sulfur and carbon dioxide, which can change climate in different ways. Too much sulfur, and you get cooling. Too much carbon dioxide, and you get warming. The balance is tricky. If a bunch of volcanoes erupted close together, they might have flooded the sky with sulfur. That could block sunlight, drop temperatures, and make the world suddenly colder. It's happened before, just usually not quite so fast. Still, with the records we have, it's hard to pin everything on volcanoes alone. The clues are there, but not enough to close the case. Let's look deeper. Beneath volcanoes, the planet is always moving. The surface of Earth is broken into giant slabs called plates. They slide, crash, and pull apart. When they grind against each other, they build mountains. When they pull apart, cracks open and sometimes let out huge bursts of magma. This movement changes more than landscapes. It can shape the climate too. When plates shift, they can cut off ocean currents, raise new mountains, or open up new paths for water. Over thousands of years, these changes matter. But could they move fast enough to cause a sudden freeze? For the most part, plate shifts are slow. You wouldn't notice them in a lifetime. But earthquakes and undersea volcanoes can sometimes cause big changes in days or weeks. If a huge quake triggered landslides under the sea, it might have blocked or redirected a key current. That could have changed how heat moved around the planet. There's a theory about giant underwater landslides called submarine landslides. Picture an underwater avalanche. These can move huge amounts of mud and rock. If one happened in the right spot, it could have plugged the path of a warm ocean current. The water would slow down, cool off, and maybe even freeze nearby areas. Did this happen during the Big Freeze? There are some signs of huge landslides in the North Atlantic from around this time. The Storegga slide off the coast of Norway is one example, but it happened later. Still, smaller slides might have played a part. Hard to say for sure. Here's another angle. Methane. Deep under the ocean floor, there are pockets of methane gas trapped in icy cages called clathrates. If ocean temperatures change, these cages can break apart. Methane bubbles up, escapes to the surface, and can change the climate. Methane is a powerful greenhouse gas. It traps heat. But if a huge amount escapes quickly, it can also mix with cold ocean water, change currents, and set off feedback loops. Some scientists have wondered if a sudden release of methane could have caused chaos in the climate systems. The records are fuzzy, but it's not impossible. Let's go back to the land for a second. When glaciers melt, they don't just release water, they also change the weight on the land beneath them. Imagine a mattress with a heavy bowling ball on it. Take the ball off and the mattress slowly rises. This is called isostatic rebound. When the ice melts, the ground lifts. Sometimes this can trigger earthquakes, landslides, or even open up new cracks for volcanoes. If enough ice melted at once, maybe the land snapped back so fast it triggered a series of disasters. Volcanoes, quakes, even tsunamis. Is there evidence for this? Geologists have found signs of sudden land shifts in parts of Scandinavia and Canada from around the right time. It's possible these movements affected the climate, at least locally. Maybe they set off a domino effect that spread farther. Now let's think about feedback loops. Earth is full of them. One small change can set off a chain of bigger changes. For example, when the ground freezes, plants die. When plants die, the soil loses cover. Bare ground reflects more sunlight, which makes it even colder. The cycle keeps going. Or maybe fires burned huge forests, sending ash into the air. The ash blocked the sun, cooled the air, and made things even worse. As the cold deepened, more plants died, leaving even more ground exposed. It's like a snowball rolling downhill. There's another feedback that's even stranger: clouds. When the air cools suddenly, clouds can trap heat or block it, depending on their type and where they form. Some models show that a sudden burst of ice or ash in the atmosphere could have shifted cloud patterns. This could have made some places much colder, much faster. Here's a twist. Sometimes, a big freeze can actually trigger warming. If enough ice forms, the world gets brighter. Ice reflects sunlight better than dirt or water. For a while, this keeps things cold. But if the ice starts to melt, dark ground shows through. That absorbs heat. Suddenly warming speeds up. It's possible that the cold snap we're talking about was part of one of these cycles. Maybe the world was swinging between cold and warm faster than we thought. Maybe the planet overshot and then bounced back. Let's get even more basic. The sun itself changes over time. Its energy output isn't perfectly steady. Sometimes it's a little stronger, sometimes a little weaker. These shifts are called solar cycles. Most are small, but if they line up with other changes, ocean currents, volcanoes, feedbacks, they can tip the climate from one state to another. Was the sun weaker during the big freeze? Some ice core records show less solar activity around this time. Maybe it helped push things over the edge, maybe not. It's hard to tease out cause and effect with cycles lasting thousands of years. We also have to think about Earth's orbit. The planet wobbles as it spins, it tilts back and forth, and its path around the sun changes shape over long cycles. These shifts are called Milankovitch cycles. Over tens of thousands of years, they control when ice ages start and end. The timing here is tricky though. The big freeze happened in the middle of a warming period, not at the end of a cold cycle. Still, if a few small orbital changes lined up with other triggers, melting ice, shifting currents, maybe a volcano or two, they could have helped flip the world back to cold. So where does that leave us? It's a mess of possibilities. Maybe it wasn't just one thing. Maybe the planet's own systems work together, pushing and pulling. A little bit of extra meltwater, a sudden shift in ocean currents, a burst of volcanoes, a wobble in the sun's energy, all stacking up until suddenly the climate flips. When you look at the records, it's almost like Earth has built-in switches. If enough knobs get turned at once, things can change overnight. What stands out is the speed. Most natural cycles are slow, but this event moved fast. That's the real mystery. How did so many pieces fall into place so quickly? Some researchers think we're missing something big. Maybe there's a process we don't see yet. Or maybe the records are just too patchy. Ancient mud, old ice and scattered bones can only tell us so much. But here's what we do know. The planet is never truly stable. Even when things seem calm, deep systems are always moving, always shifting. Sometimes they balance each other out. Sometimes they all tip the same way. This isn't just a story about ancient disasters. It's about how everything on Earth is connected. The shape of the land, the movement of the sea, the fire under the ground, even the energy from the sun. Each can push the others. Sometimes they push too far. If the big freeze was caused by Earth systems, it's a reminder that we live on a restless planet. Nothing lasts forever. Stability is the exception, not the rule. It's also a lesson about complexity. History isn't just about people or animals. It's the story of everything, rocks, water, fire and sky, all tangled up. Change one and the rest can follow. Some people find that idea unsettling. I think it's kind of amazing. We're part of a system so big, so complicated, that even after thousands of years we're still guessing at how it works. And no matter what the trigger was, water, space or Earth itself, the result was the same. The world froze, cultures vanished, animals disappeared. But here's the bigger question. What did this event do to humanity's future? So we've looked at what happened and tossed around different theories for why. But what did this sudden freeze actually do to humans? What changed for us and for the planet because of those 1,000 cold years? Let's dig in. Picture a village just before the world turned cold. People are finally settling down, not just wandering from place to place, but building homes, planting the first gardens, storing food for winter. Kids are growing up in the same spot where their parents did. Everything seems stable for the first time in ages. Then, out of nowhere, the weather flips. Summers turn short and bitter. Frost comes earlier each year. Harvests fail. Rivers freeze longer. The world they knew is gone. People can't just wait for it to get better. They have to move, change, or risk dying out. Archaeologists have dug up clues from sites all over the world. In the Middle East, right where some of the earliest villages stood, you can see the story in the dirt, layers of ash from fires, unfinished houses, tools abandoned mid-use. It's like someone hit pause on the birth of civilization. One famous spot is called Abu Huraira. It's in modern Syria. Before the cold, people there had started growing wild grains. They were getting close to real farming. But when the freeze hit, the site changes. Suddenly, there's more evidence of hunting. The bones of wild animals pile up. The grains disappear for a while. People went back to old ways because the new one stopped working. And it wasn't just there. At Natufian sites in the same region, you see the same thing. The first signs of farming vanish from the ground. People leave, some come back centuries later after things warm up again. It's like history rewinds. Why does this matter? Because it shows that the cold didn't just push humans to the edge. It stopped one of the most important changes in our story, farming. The invention of agriculture is what let us build cities, write, invent money, and all the rest. But for 1,000 years, the planet slammed the brakes. This delay changed everything. Before the cold, people were starting to settle all over. In the Middle East, in parts of Asia, maybe even in the Americas, permanent homes were popping up. But when the climate flipped, most of those early experiments failed. People had to move, adapt, or just try to survive. Let's zoom out. In Europe, the same pattern repeats. Groups that had begun to settle abandoned their camps. Forests shrank. Grasslands took over. People followed the animals, moving south or finding new places to live. Some cultures vanished from the record for centuries. In Asia, you see signs of stress too. Ancient campsites in Siberia and Mongolia show fewer tools and less variety. The bones of food animals drop off. Some sites disappear completely for hundreds of years. It's like entire groups just melted away. But here's where it gets really interesting. In some places, people didn't just survive. They changed. They invented new ways to cope. In the Middle East, for example, some groups started grinding wild seeds that grew even in the cold. Others learned to hunt smaller, faster animals. In some cases, they built stronger shelters, dug deeper storage pits, or found ways to keep warm. Think about what that means. Faced with disaster, humans didn't just give up. They got creative. Some of the first bread in history may have come from, this time, flat cakes made from crushed wild grass seeds, not because they wanted to, but because the old foods were gone. Let's talk numbers. Archaeologists have counted the bones at ancient sites and found huge drops in population. In some regions, up to 70% of people seem to vanish from the record. Whole families, maybe whole tribes, gone. Nobody knows if they died, moved, or just left no trace. But the effect is clear. The world emptied out. This wasn't just in one place. From Spain to China, from Egypt to Canada, you see the same pattern. Less variety in tools, fewer homes, more signs of struggle. Even the artwork changes. Before the cold, you find cave paintings, carved beads, little statues. During the freeze, art almost disappears. Maybe people were too busy trying to survive. Maybe they lost the time or energy for beauty. And yet something else appears. New kinds of stone tools show up. Smaller, sharper blades. Tiny arrowheads called microliths pop up across Europe and Asia. These weren't for hunting mammoths. They were for catching rabbits, birds, fish, smaller game that could survive the cold. People were switching tactics. Fast. Now, let's look at Africa. You might think it was untouched, but even there, the climate shifted. Some lakes dried up. Grasslands turned to desert. People living in the Sahara moved south. In places like Lake Victoria, Ancient shorelines show water levels dropping fast. Animals changed their ranges. People had to adapt, just like everywhere else. In South America, the same story unfolds. Evidence from ancient camps in the Andes shows people moving up and down the mountains, following the climate bands as they shifted. Some groups abandoned high-altitude sites and moved lower, looking for warmer ground. Everywhere you look, the message is the same. The freeze hit the reset button on human progress. It scattered people, wiped out early experiments in farming and settlement, forced everyone left to get creative or disappear. But there's another side to this. When things finally warmed up, the changes didn't just go back to normal, they accelerated. The first true farming villages pop up almost everywhere at the same time, about 9600 BCE. In Turkey, you get places like Göbekli Tepe, with its giant stone pillars. In Jericho, you see the first real city walls. In China, the earliest rice paddies appear. In Mexico, people start growing squash and beans. It's as if the long cold forced humans to rethink everything. When the world finally warmed, they were ready to explode into new ideas. Maybe the struggle made us smarter, or at least more flexible. Maybe it weeded out the old ways that couldn't handle change. Let's get back to the animals for a second. We already talked about the big ones that vanished. But what about the ones that survived? Deer, bison, wild horses, antelope. These animals became the backbone of new hunting strategies. People learned to track smaller herds, set traps, and use every part of the animal. Some groups even started to herd animals, a step toward domestication. Dogs probably became our partners around this time too. The oldest dog skeletons show up in sites from just before, during, and after the big freeze. Maybe people and dogs stuck together, helping each other hunt and stay warm. It's hard to say for sure, but the timing is suggestive. Now, let's talk about plants. Wild grains were everywhere before the cold. Afterward, the ones that survived were the toughest. People learned which ones could handle drought, frost, and poor soil. When farming began again, it was with these hardy plants. Wheat, barley, millet, rice. All were shaped by the long years of struggle. Even our bodies may have changed. Some scientists think people got shorter in colder regions, a trick to keep warm. Bones from this time show more signs of stress, breaks, infections, missing teeth. Life got harder, but it also made us tougher. What about technology? Before the freeze, stone tools were big and simple. Afterward, you see more variety. Tiny blades for small game, fishing hooks carved from bone, sewing needles show up, maybe for making warmer clothes. In cold places, people built houses partly underground, using earth as insulation. Fire became even more important. In some places, you find thick layers of ash from ancient hearths. People may have kept fires burning for weeks at a time, never letting them go out. In the far north, some groups learned to use animal fat for lamps, bringing light and warmth into the darkest winters. Let's not forget about community. When times are hard, people often band together. Some sites from this time show large shared shelters, maybe for several families. Food was probably pooled. Stories and songs passed the time during long, cold nights. The bonds that kept people alive got stronger. But there's a darker side. When resources are tight, conflict can get worse. Some ancient skeletons from this period show broken bones that healed badly, or wounds that look like they came from weapons. Maybe fights broke out over food or shelter. Maybe strangers were seen as threats, not friends. Still, cooperation seems to have won out in most places. The groups that lasted were the ones who shared, adapted, and learned from each other. When the world warmed, these survivors were ready to build the first real societies. Let's talk about memory. Imagine living through this time. Your grandparents told stories about a world full of animals, green forests, and easy food. You grow up in a world of hunger, cold, and constant movement. When things get better, those old stories become legends, myths of a lost golden age when the world was easy and people had all they needed. You can almost feel the roots of later myths, like the Garden of Eden or the idea of a great flood, growing out of real memories from this time. Some researchers think the trauma of this period left marks on our stories, our art, even our genes. Maybe it made us more anxious, more driven to plan ahead, store food, build walls, and prepare for disaster. Maybe it's the reason we're always looking for patterns in nature, trying to predict what comes next. Now let's look at the land itself. The freeze didn't just change people and animals, it reshaped the planet. Glaciers scraped away soil, rivers cut new paths, wind blew dust across continents, burying old camps and making new ones possible. In some places, thick layers of dust called loess built up, making the ground rich for future crops. In others, forests died back and were replaced by grasslands. When the world warmed, these changes stuck around. New lakes formed, old ones vanished. The places where people could live shifted forever. Some of the best farmland today, like the black soils of Ukraine or the Loess plains of China, were created or improved during this time. So when you look at the big picture, you see a world reset, not just in climate, but in everything. People, animals, plants, landscapes, all forced to start over, all shaped by a disaster nobody could have seen coming. But here's something that keeps coming up. Why did some groups survive while others vanished? It wasn't just luck, it was flexibility. The groups that tried new things, new foods, new tools, new ways of living, were the ones who made it. The ones who stuck to old habits faded away. This is the lesson that echoes down to us. Change isn't always slow and gentle. Sometimes it's a slap in the face. The world can shift in a handful of years, and everything you thought was solid melts away. But if you bend, you don't break. Scientists are still finding new clues. In South Africa, cave sites show people making tiny stone blades during this cold period. In the Americas, you see the rise of different toolkits, each tuned to new animals and new lands. In the Middle East, you find the first evidence of storing wild grains in pits, maybe as a hedge against bad years. Everywhere, the survivors were the inventors. Even language may have changed. When people scatter and regroup, their words shift, dialects split, new ways of talking appear. Maybe this is when some of the language families we know today first took root. So what did the big freeze mean for human history? It was a test, a hard, painful, drawn-out test. It killed dreams, ended cultures, and wiped away old ways of life. But it also forced us to adapt, to try new things, to become the kind of species that could survive anything. And when the cold finally ended, the world was ready for something new. Farming, cities, writing, trade, all were waiting in the wings. The survivors were the ones who built our future. That's why this story matters. It's not just about disaster, it's about resilience, about how humans can take a blow, stumble, and get back up stronger. It's a reminder that even the darkest winters end. And when they do, the world blooms again. Now, the big freeze is over. But what it revealed about our planet and about us is still shocking. Because what happened next changed everything, all over again. The cold finally ended. The world began to warm, ice melted, and the land changed. But the real shock is what came next. The period after the big freeze wasn't just a return to normal, it was a leap. Everything moved faster. People, plants, animals, even the land itself. Nothing was quite the same again. Let's look at what actually shifted, not just in the environment, but deep inside human culture. This is where the story gets personal, because it's about how disaster shaped what we are now. Take farming. Before the cold, it was just getting started. Grain was gathered, sometimes planted, but not really tamed. After the long freeze, real agriculture exploded. Villages grew larger. People tried new crops. In the Middle East, wheat and barley became the backbone of diets. In China, rice paddies appeared in the Yangtze Valley. In Central and South America, squash and beans took root. This isn't just a story of plants, it's one of timing. Farming began in several places almost at once, right after the cold ended. Not over thousands of years, but in a few hundred. Some scientists call this the Neolithic Revolution. But don't let the term scare you. It just means people started living off the land in new ways. Why did this happen so quickly? Here's the puzzle. The knowledge of how to grow and store food probably existed before, but harsh weather stopped people from using it. When the climate smoothed out, the old ideas came rushing back better than before. It's like the world had been on pause, waiting for a chance. But there's more. The animals people hunted also changed. Mammoths, mastodons, and saber-toothed cats were gone. Instead, herds of deer, antelope, and wild cattle spread across the grasslands. These animals were smaller, faster, and harder to catch. People who survived learned to hunt differently. They built traps, used nets, and worked together in new ways. One of the biggest shifts was toward herding. The earliest evidence of people raising sheep and goats comes right after the cold. At first, wild animals were followed and protected. Over time, people started keeping them in pens, helping them survive winter, choosing the friendliest or strongest to breed. Soon, these wild animals became the first livestock. Dogs played a role too. They may have helped guard flocks and warn of danger. Some of the oldest dog burials in the world date from just after the freeze. There's even a grave in Germany from about 12,000 years ago, where a young person and a puppy were buried together. It hints at a deep connection between people and animals, a partnership that may have helped both survive. Let's talk about homes. Before the cold, houses were simple: wood frames, animal skins, maybe some stones. Afterward, you see something different. In places like Jericho, people built thick walls out of mud brick. They dug deep storage pits lined with clay or stone to keep food safe from weather and animals. Some villages had stone towers, maybe for defense or as a symbol of working together. These weren't just shelters. They were signs of a new kind of life, one that was more stable, less likely to be wiped out by a bad season. The way people organized themselves changed too. Large groups needed rules. They needed leaders, plans for sharing food, and ways to settle conflicts. Some archaeologists point to early signs of councils, shared storage, or even the first hints of government. Not kings or queens, but elders or respected hunters making decisions for the group. Let's move to art. During the cold, art almost disappeared. People were moving too much, struggling too hard. But as soon as things warmed, creativity surged back. Painted walls, carved statues, jewellery made from shells or bone. In Turkey, at a place called Göbekli Tepe, people hauled huge stones into circles and decorated them with animals and symbols. Nobody had ever done anything like it before. Why would people build stone circles or make art when life was still tough? Maybe because art and ritual helped people feel connected, gave them hope, or helped groups stick together. Maybe it was a way to remember the past and imagine a better future. These early temples and artwork suggest a new kind of thinking, one that reached beyond just surviving toward meaning and memory. Now let's talk about the land itself. The cold had scraped away forests, dried up lakes, and left bare ground in many places. But as things warmed, plants rushed back. Grasslands spread across Europe and Asia. Forests grew in North America and China. In Africa, the Sahara shrank for a while, turning into green savanna. Animals followed these changes and so did people, but it wasn't just about returning to old patterns. The soil itself had changed. In some places, dust blown during the freeze made the ground richer. These new soils became some of the best farmland on Earth. In Ukraine, China, the American Midwest, thick, dark dirt made it easier to grow crops. The disaster had, in a strange way, prepared the land for farming. Let's pause here. Imagine living through this time. Your grandparents told stories of hunger and cold. You see the world warming, green returning, animals coming back. You're trying new things, planting seeds, building better homes, working with neighbours, making art. Everything feels possible, but also uncertain. This is where the big questions come in. Why did humans bounce back so strongly? What made us different from other animals that vanished? It wasn't just brain power. Other animals are smart too. It wasn't just tools. Even birds use sticks or stones. A big part of it was something simple. The ability to remember, share, and build on ideas, culture, language, the power to teach kids what worked and what didn't. The cold years forced people to invent, but the warm years let them pass those inventions down. That's how progress happens, not just by luck, but by learning and sharing. Let's talk about risk. The freeze taught people to plan for bad times. They started storing food, grains, dried meat, nuts. They dug pits, built granaries, and learned to save for winter or drought. This habit stuck. Even today, people everywhere keep pantries, root cellars, or just a little extra in the cupboard. It's a lesson from ancient fear. But there's another side to this. The trauma of the cold may have changed how people thought. Some researchers think it made us more anxious, more focused on safety and control. You see signs of this in myths and stories from later times. Legends of floods, endless winters, or golden ages lost. Maybe these tales started as memories of a real crisis passed down for thousands of years. Now let's zoom out and look at the world as a whole. The end of the cold didn't just trigger farming in one spot, it set off a chain reaction. In the Middle East, China, Mexico, and the Andes, people began experimenting with crops and animals at almost the same time. They had different plants and animals, but the pattern was the same. Settling down, building villages, inventing new ways to survive. It's hard to explain how rare this is. For hundreds of thousands of years, humans lived mostly as small bands of hunters and gatherers. Suddenly, in less than 1,000 years, villages, farms, and even towns pop up on every continent except Antarctica. It's like humanity got a jump start. Let's get specific. In the Middle East, settlements like Çatalhöyük and Jericho grew to thousands of people. In China, early villages along the Yellow and Yangtze rivers became centers for rice and millet farming. In the Americas, sites like Guilanaquitz in Mexico and Guitarrero Cave in Peru show early experiments with squash, beans, and potatoes. None of these places had contact with each other, but the pattern repeats: disaster, then invention, collapse, then rebuilding. It's as if the cold taught people everywhere the same lesson. Don't wait. Try everything, and never trust that things will always stay the same. Now let's talk about human bodies. There's evidence that people's health changed after the cold. Bones from before, the freeze show signs of hunger, disease, and hard lives. Afterward, things improved, for a while. Diets became better, with more reliable food. But as villages grew, new problems appeared. Crowded towns meant disease spread faster. People's teeth show more cavities, maybe from eating more grains and less meat. Life got easier in some ways, harder in others. What about relationships? Settled life changed families. Before, small groups moved together, often related by blood. After, villages mixed strangers and friends. Marriage patterns shifted. People had to learn new rules for sharing, fighting, and making peace. Maybe this is when big family groups, clans, or even villages started to matter, more than just close relatives. Let's look at technology. Inventions multiplied after the cold. Pottery appeared, useful for storing food, cooking, and even for trade. The first woven fabrics show up, probably made from flax, cotton, or wool. People built boats sturdy enough to cross lakes and rivers. In some places, you see the first wheels and carts. Trade networks grew. People carried obsidian, shells, and other valuable things hundreds of miles. This meant new ideas and inventions spread quickly. If someone figured out how to make better pots or sharper blades, word got around. Let's not forget about writing. It didn't appear right away, but the roots go back to this time. People started making marks on stones, bones, and clay. Maybe they were keeping track of food, marking ownership, or telling stories. The idea that you could record something for later was a huge leap. Now, think about belief and spirituality. With bigger groups and more settled life, rituals became more public. Early temples, stone circles, and burial mounds all date from this period. People buried their dead with care, sometimes with food, tools, or jewellery. Maybe they hoped for another life, or just wanted to honour ancestors. The idea of a shared past and maybe a shared future became important. Let's talk about conflict. As people settled, fights over land, water, and food grew. Some of the earliest signs of war come from this time. Villages burned, skeletons with wounds from weapons, walls built for defence. But you also see signs of peace. Villages trading, people buried together peacefully, art that celebrates sharing and cooperation. The natural world was still unpredictable. Even after the cold ended, weather shifted. Droughts, floods, storms. These could ruin a village or wipe out a crop. People learned to watch the sky, track the seasons, and predict what might come. Some of the first calendars appear in these early farming villages. The cold years left a mark on the land, on people's bodies, and deep in their memories. But they also set the stage for everything that followed. Farming, cities, writing, nations. The old world was gone, but a new one had begun. So, what does all this mean for us now? Here's the simple truth. The Big Freeze wasn't just a disaster, it was a turning point, a hard reset that forced humans to adapt or disappear. The ones who survived weren't the strongest or the smartest. They were the most flexible, the most willing to try something new. You can see echoes of that time in the world today, in the foods we eat, the way we farm, the stories we tell, and even in the way we plan for the future. The lesson isn't about fear, it's about hope and invention. We're the children of survivors. Our ancestors faced the worst cold in the memory, lost almost everything, and then started over. They tried new ideas, built new homes, and found new ways to live. That spirit, the drive to keep going, to rebuild, to imagine a better future, still lives in us, and maybe that's the real legacy of the Big Freeze. Not the hardship or the loss, but the proof that even after the darkest winters, there's always a new spring. As the world turned warm again, people everywhere felt the same pull, to settle down, to build, to dream. And in those dreams, you can still hear the echo of 1,000 cold years, a whisper to keep moving forward, no matter what. If you step back and look at the story of the Younger Dryas, it's not just about a cold snap, or even survival. It's about how close everything came to ending, and how much depended on what happened next. This was a real-life reset. The whole world got shuffled. It's wild to think how much of what we call civilization depends on a few lucky breaks after a disaster. Let's unpack what that means. Imagine human history as a long line stretching back in time. For most of it, not much changes for thousands of years. People hunt, gather, move with the seasons, then suddenly the world gets knocked off course. Ice returns, the weather turns brutal, and nearly everything stops. People are scattered, cultures break apart, animals vanish. It could have been the end of the story, but it wasn't. Humans found a way to keep going. They didn't just wait for the weather to get better. They figured out new ways to live. When things warmed again, they remembered old skills and invented new ones. Farming, building, trading, even believing. These things came roaring back, stronger than before. It's almost like the hard times squeeze people into trying things they never would have tried otherwise. You see this in the way people started experimenting. They tried growing crops in places they hadn't before. They built different kinds of homes. They made tools from new materials. They traded things farther and faster. They painted, carved, and dreamed in bigger ways. The freeze didn't just knock people down, it made them get creative. The pattern shows up everywhere, not just in one place, but all over the world. Groups that had never met, living thousands of miles apart, all did something similar at the same time. That doesn't happen by accident. It tells you there was something about being pushed to the edge that made people leap forward. It's easy to forget how much of our world is built on these moments. The crops we eat, the animals we raise, even the shape of our towns. So much of it started because people had to adapt after a disaster. If the weather had stayed steady, maybe people would have kept living the old ways for thousands more years. Instead, the cold forced a change, and that change made everything else possible. Let's talk about memory. Stories from this time echo in legends and myths around the world. Flood tales, heroes who survive endless winters, golden ages lost and found. For generations, people carried these memories. They didn't have writing yet, so they used stories. These tales shaped how people saw the world. They reminded everyone that things could collapse without warning, but also that there was always a way through. That's a deep lesson. The cold didn't just make people tougher, it made them remember. It made them plan. It taught them to save, to work together, to watch the sky and the land. Those habits didn't disappear when the ice melted. They became part of what it means to be human. Now think about risk and reward. After the freeze, people took more chances. They tried planting new seeds. They built bigger homes and villages. They explored past old boundaries. Sometimes it worked. Sometimes it failed. But the willingness to risk, to step into the unknown, is what kept people moving forward. That's a spirit that still shows up today. The freeze also changed how people saw time. Before, the world seemed steady, almost endless. Seasons came and went, but big changes were rare. After the disaster, nothing felt certain. People learned to pay closer attention. They tracked the sun, the moon, the stars. They watched for signs of change. This is where the first calendars started. It's where the idea of planning ahead got its teeth. It's not just about survival or farming, it's about imagination. The first art after the freeze is bold. Animals carved into stone, circles of pillars, symbols no one today can fully explain. These weren't just decorations. They were ways to make sense of a world that had flipped upside down. When people make art in hard times, it's a form of hope. It's a way to say, we're still here. We matter. Let's look at the bigger picture. The cold taught humans a strange lesson. Nothing is permanent. No animal, no way of life, not even the weather itself. That's scary, but it's also freeing. It means you're not trapped by the past. You can try something new. You can start over. This idea, resetting, inventing, rebuilding, became the heart of human progress. There's another side too. The freeze left scars. It made people more cautious, sometimes fearful. You see that in how people built walls, stored food, and told stories about loss. But out of that came wisdom. Don't take anything for granted. Have a backup plan. Work with your neighbours. These lessons helped people survive later disasters. What does all this mean for us now? For one thing, it's a reminder that change isn't always gentle. Sometimes the world throws you a curveball. Sometimes it's not fair. But humans are wired to respond. We're not the biggest or strongest creatures, but we're good at learning, sharing, and trying again. That's our real superpower. You can see the echoes of this old crisis in lots of things today. In the way we build cities, in the foods we eat, in how we tell stories about the past, even in the way we worry about the future. The lessons from this time are still with us, tucked into the corners of daily life. Maybe the most important thing is this: disaster doesn't have to be the end. It can be the start of something new. The people who survived the freeze weren't just lucky. They were brave. They were willing to try, to fail, and to try again. That's the real secret of our history. So next time you look at a field of wheat, or a city skyline, or even a painting on a wall, remember, these things exist because people faced the worst and then built something better. The story of the Younger Dryas isn't just about ice and struggle. It's a story of hope, invention, and starting over. And that's a story that never gets old.